Data Analysis Part 7. Applications of Mathematical Probability to make predictions and inferences in real problems. Right, hello everyone, welcome to Part 7 of the Data Analysis course. In the previous two parts we introduced the definitions and a notation of probability for the purpose of doing data interpretation. We introduced the laws of probability and then the concepts of joint probability of two events and the conditional probability of one event given that another one has occurred. And we're interested in making use of this to learn to make predictions given the event that has occurred is some data and we know all about it. What can we say about future events, or what inferences can we draw? What can we say about conclusions about the state of the real world? So in order to do this, I said that as well as the notation of conditional probability, and as well as taking that and manipulating it into Bayes' rule, we will want to make use of two concepts that we have talked about already, but which we shall recap. First is the principle of indifference, and the second is the law of total probability. So between them and the laws of probability and Bayes' rule, that's all of the theoretical material that should be needed in order to make good predictions or to do good data analysis. Beyond that, we just need to look at examples of how to actually use that. So the principle of indifference is useful because sometimes we will need a starting point for some work, or we will need what might be called a prior probability, a degree of belief in some statement before we receive any data about it. And it's very useful if we have events or outcomes for which we have what's called technically indifference, or you could say equal certainty. What this means is that if we have an equal amount of evidence in support of some statements, then those statements should have equal probability. If they also form a comprehensive list of possible outcomes, then that's good because the total probability of each of them added up, or all of them added up, according to the using the law of probability to do that adding up, the third law. If they're all of equal probability and the list is comprehensive, and there's n such possibilities, then the probability of each one is simply 1 over n. In any case, so what is an example of a situation where we have indifference? You would say, for example, given a shuffled deck of cards and you know nothing more about the arrangement of the cards in the deck, you would say that the probability of drawing an ace, or of a king, or of any other particular valued card is equal at 1 over 13, for example. This is, as I said, this is the probability, your degree of belief based on the information available to you. For somebody else who happens to have had a look at the deck of cards and look what card's about to be drawn from the top, they would have complete certainty about what it's going to be. And they would be in a different situation because the information available to them is different, so of course the probability for them is different because probability is computed from the information that you have available. So principle of indifference, if in some examples coming up we can say we are indifferent about two hypotheses, that's a technical property and it means they've got to have the same probability, and that might be useful in the examples we have coming up. The second manipulation that we will want in the real world, in addition to the principle of indifference and your laws of probability and your concept of conditional probability and Bayes' rule, is the law of total probability in section 5.2. So this is what we need when we need to quantify our certainty in a statement which itself depends on which other possible statements are true. In this case, we can add up the probabilities based on other cases using the law of total probability. I'll introduce this with a particular example, but then it will be easy to see how this generalizes to anything. The particular example is 5.2a. Imagine that you are in a chess tournament and that your next game will be against either Anne or Bob. And you have established your probability of beating Anne as 0.2 and of beating Bob as 0.7. However, slightly unfortunately, the probability that you're facing Anne is much bigger than that you're facing Bob, and it's 0.75. What then do you say is the number for your probability of winning the game? If you sit and think about this intuitively, you will probably add it up correctly. But let's see mathematically why it follows the formula that you probably would use intuitively, and what that formula is. So to solve this problem, you need some notation. W is the event that you win your game, and A is the event that you are playing against Anne. Obviously, since in this situation it's either you're playing Anne or Bob, then the event not A means playing against Bob. So you just use some algebra. We can say that 5.2b must be true. Your event W, your list of outcomes in event W, is the union of two smaller lists of events. W means winning, so if you take the union of winning against Anne and winning against not Anne or Bob, that must give you the total list of outcomes where you win. Because of the Law of Probability 4.4c, we said that the probability of the total probability of two mutually exclusive events is the sum of the probabilities for those individual events. We can apply that principle to this example as equation 5.2c. We can also go up and see in the previous chapter we obtained the multiplication rule, which describes the probability of the intersection of events W and A. We said the probability of winning against Anne, or the intersection of W and A, is this conditional probability, winning if you are playing Anne, times by the probability that you're playing against Anne. We can plug those equations, we can plug 5.2d into equation 5.2c, and we can plug the not Anne version of equation 5.2d into the other side of equation 5.2c, and you then get your law of total probability for this particular example, 5.2e, that you have this algebraic expression: your probability of winning a chess match is the sum of two conditional probabilities times weighted by the probability that each of those conditions is actually happening in the real world. So you should end up, if you consider this problem intuitively, you should have found that your total probability of winning was 0.7 if you're facing the easier player, Bob, so 0.7 times the 0.25 chance that you're facing Bob, plus 0.2 times the 0.75 chance that you're facing Anne. You should add those up and you should say, my total probability of winning my next game comes out as 0.325 in this particular example. Now, the general case that we're looking at is the law of total probabilities as written in equation 5.2g. So the fundamental idea is that your universe of possible situations is split up into mutually exclusive cases. In the particular example, it was facing Anne or not. If needed, you could imagine splitting up event not A arbitrarily further, so that you could end up in the chess tournament with a comprehensive list of the possible players that you might face in your next chess game. And you probably wouldn't then list their event names, naming them after people. You'd probably get a list of hypotheses, H1, H2, H3, which make up a comprehensive set of events which subdivide the universe of the situations relevant to quantifying your certainty in W. Or in other words, H1, H2, H3 in the chess match would each be you're facing a particular opponent, and you would take those probabilities and use them to weight the conditional probability that you win against each component, to each opponent, to get a total probability that you do win. This law of total probability, you should make sure that you're happy about where this comes from, because then we're going to want to use this to explain some real situations. So, in the next two sections of this video, next two sections of the lecture notes too, I want to look at applying the law of total probability and the rest of the probability maths we've looked at so far, so definitions and Bayes' rule, in order to explain and make predictions in two different example situations. Section 5.3 will be a simple example situation where we will only need to consider a small list of hypotheses, H1, H2 and H3, and section 5.4 will consider what do we have to do in the real world when we need a longer list of hypotheses, and in fact we'll look at how we might approximate the real world into a manageable list of hypotheses in order to make predictions using a simple computational method rather than having to deal with the harder maths for lists of continuous possibilities. So simple example first, 5.3. A model for the probability of event arising from a small number of hypotheses. So this example is going to be the well-known but useful in textbooks Monty Hall problem. So this is statistical inferences which can be made successfully. We can get good explanations by considering a small number of hypotheses. In 5.3a, the Monty Hall problem, this is a description about a game show or some gambling problem. So there is a prize, which is a car in the traditional version of the game, hidden behind one of three doors. We don't know which, as the observer. We do know that behind the other two doors there are goats, and the clear implication is you don't want those, you want the car. In the standard formulation of the problem, we are told something. We're told a situation, and in fact, the key to understanding why this is sometimes given as a puzzle is that the stated form of the problem, which is this second part of, well, it's 5.3a, we actually need to add a little bit of information in order to fully answer this problem. So in 5.3a, we have these doors. One of them has a prize. You pick a door, which we will say is door number 1, and then the host, who does know what's behind the doors, opens door number 3 and reveals that it hides a goat. And then the host asks you, do you want to switch to pick door number 2? And then the puzzle question, or the reasoning we need to do, is to answer, is it to your advantage to switch your choice? So probably you've heard about this problem, and probably you've heard the description, the famous saying, well, you should always switch. Okay. The key to understanding why the Monty Hall problem caused a controversy in the newspapers when it was posed is that the question as it's normally posed is incomplete, and in order to complete the question you need to add some information which makes an exact mathematical statement about how it was the host selected a door to reveal. Now, if you've watched the game show, if you have some common sense about game shows, you will probably you can fill in that the way the host chooses a door to reveal is this additional bit of background information, 5.3b. The way this works, which is necessary in order to make the game reliably entertaining, is that the host, Monty, opens a door that, first of all, was not chosen by the contestant, and B, does not hide the prize. So in that situation, it's easy to apply Bayes' rule and total probability to explain the answer that it is to your advantage to switch your choice. We'll just talk through this. You may well have seen this before, but you need to know how this is presented algebraically, and you need to follow this through so that you can in your assignment, as a quick starting question for your assignment, explain what happens if your assumption is different about how the host chooses a door to reveal. So that is what you will get to do, and I will leave you to think about that version of it. But the resolution of the problem using Bayesian reasoning, and the standard form of the problem, where the background information is 5.3b, as well as the description of what's happened, 5.3a. Let's introduce some notation. Let's say that the notation C1, C2, and C3 means that the car is behind doors 1, 2, or 3, respectively. Let's have an additional bit of data. D is the data that the host revealed a goat behind door 3 after you selected door 1. So we can use the things that we've looked at so far. We can clearly apply the principle of indifference. So as far as we are concerned, we have no information at the start of this game, before the host has revealed the door to us. We had equal information or symmetric information as to the car being behind each door. In other words, we don't know anything. That's a way of saying we have equal information. So we can say indifference applies. Probability of C1, C2, and C3 must be equal, and because they form a comprehensive universe, they have a total probability of 1, so they must each individually have a probability of 1/3. So we get that as equation 5.3e. Given the standard assumption about the host's behavior, described in 5.3b, we can write down the conditional probability of of receiving the data D, that the host revealed a goat behind door 3, given that we stated that we were interested in door 1. We can write down the conditional probability of that data under each of the 3 possible hypotheses about the car being behind door 1, 2, or 3. So first of all, under hypothesis 3, that the car is behind door 3, then it's impossible to get the data that the host revealed a goat behind door 3. So that probability is 0. If the car is actually behind door number 2, and we chose door number 1, then the host, Monty, had no choice. It was certain that he must reveal door number 3, according to his definition of behavior 5.3b. So probability of data given C2 is 1. If C1 was true and the car is actually behind door number 1, then the host had a free choice between opening door number 2 or door number 3, and so we can be indifferent about his choice there because we don't have any reason to think he favours one or the other. So those are the 2 possibilities, and from indifference we say each of them has probability half. In other words, the probability of the data that we received is a half. So you should be happy about where these come from algebraically, because once you've written these down, we can apply Bayes' rule and the law of total probability quite mechanically and easily to explain the answer to this problem in its normal form. We can apply Bayes' rule, and we're interested in the probability that the car is behind door 2, probability of C2 given the data we've received. Well, apply Bayes' rule, 4.6c, I think, and you get this expression 5.3g, and the probability of the data is very straightforward to obtain. How do I get the probability of the data? Well, I've got my list of hypotheses, C1, C2, and C3, and I just apply the law of total probability we introduced in the last section to those possible small list of situations with the conditional probability of D in each case, and I get the probability of D. It comes out as a half, 5.3h. So I've got all the numbers I need to put into Bayes' rule, and I have, given the data that I've received in this standard version of the question, the probability C2 that the car is behind door 2 comes out as 2/3. You should be able to follow that through numerically. You should also be able to find the probability that it's behind door 1, and that should come out as 1/3. So under that standard version, then yes, that's sort of why you famously always switch in the Monty Hall problem. But there are non-standard versions of the Monty Hall problem. The reason why this is presented as a lateral thinking problem in newspapers, or why people, and when it is, people can argue over it, is because usually when the problem is explained to people, no actual strict definition is given for the assumption about the way the host chooses a door to reveal. The one which actually applies to the game show is generally accepted after a lot of argument to be 5.3b, because other ways of choosing doors would often not make for a good game. Nonetheless, it's completely possible that the host did something else. So in your assignment, I would invite you to consider what would happen if, well, you're in a game where you get the observation as described here. You choose door number 1, and as it happens, the host opens door number 3, revealing a goat, and asks if you want to swap for door 2. But what would happen? What would be the probability that the car is behind door 2 if instead the host, as it happened, had drawn at random out of a hat which door to reveal, and it so happened that it was one you didn't pick and which revealed a goat? That would give a different description of whether it's to your advantage to swap, and you can think about that particular version of the problem. There are other exotic variations, but they start to push the limits of what is interesting to discuss for this case. We've used here an Bayesian reasoning to answer or to explain a situation that has a small number of hypotheses. The key principles of Bayesian reasoning are these, from 5.3j. Always write down the probability of everything. It should then become apparent when you start to use Bayes' rule to solve if you're missing a probability. You need to write down the probability of the underlying hypotheses, in this case C1, C2, C3, and also the conditional probability of getting the data given each of the underlying hypotheses, so 5.3f. If you can do that, you can solve any simple problem, any simple bit of Bayesian reasoning. So we'll go on in the next slide to look at applying Bayesian reasoning in harder and, in fact, real-world problems of many kinds. And this will be called a model for proportions, which I'm going to explain using my my sample problem for this course about the nice couples from Lake Wobegon, but this can actually be applied to a large number of things you might need to understand. Right. So, the general strategy that we want to use for more complex problems than the Monty Hall problem, it will be something like this. Let's apply it to a particular problem. So, you have some data that you have met exactly one couple from the town of Lake Wobegon, and you thought they were nice. So the question is, what is the probability that most couples, so more than half of the couples from this town, are nice? What is the difficulty in processing this observation? Is that the data you receive, you met one couple and they're nice, might occur in many different underlying situations, where one underlying situation might be, well, 1 in 10 of the couples are nice, another underlying situation, 7 in 10 of the couples are nice, and so on, and so on. A potentially large list of underlying situations, obviously each of which is going to be approximately enough true, because I've divided it into just 10% bins. That's the strategy that we want to take for this type of problem, and for a lot of problems. This would also apply, for example, to will tennis player A beat tennis player B in their next match, given that in the most recent one match they did. and it would also apply to will a industrial part be within specification, given that we've previously looked at one and it was. So it will apply to a large range of real-world problems. The strategy that we'll use in general is this. So we write a comprehensive list of hypotheses. We use Bayes' theorem to compute the new probability of each hypothesis given the data, and then given the new probability for each hypothesis, we compute the total probability for the statement we want to know about, using what we know about the list of hypotheses. So this is written up in the notes in section 5.4, and here, just to say it again with a little bit more mathematical detail. So we're going to have some problem, and we're going to, number one, write a list of underlying hypotheses. If each of these underlying hypotheses is equally certain, and we can use the principle of indifference, then that's great, because it makes it easy to write down a prior probability for them, your probability of, say, C1, C2, C3. The list of hypotheses must be comprehensive, or at least when we treat them as approximations of the real world, we must not be missing a big range of possibilities that might happen. And each hypothesis must allow a fairly exact probability to be assessed for each possible observation. And how might it be assessed? Well, it might be assessed using the principle of indifference. We'll see this in practice in a bit. Once you've done that, that's most of the thinking has been done. You need to do 5.4e. You need to assess the prior probability for each hypothesis. You need to do 5.4, I've listed this as double E to insert an extra step I forgot. You need a model to provide the probability of the data conditional on every hypothesis. So in each hypothesis, you need to have some way of saying how likely it is that you got the data you did. 5.4f, then you'll be applying Bayes' rule mechanically. You'll get the new probability of each hypothesis, and then 5.4g. Using the new probability for each hypothesis, probably you'll need to take that and get, using the law of total probability, the probability for the statement you're interested in. Right, so let us apply this method to my demonstration problem about Lake Wobegon, and we do that by considering the behaviour in, well, we consider a list of hypotheses written here as equation or statement 5.4i. So I need, first of all, a list of underlying situations which might be true. So I'm going to call these hypothesis H0, H1, H2 up to H10. These are 11 different hypotheses. I could call them H subscript I. Each one is that the proportion of couples in Lake Wobegon who are nice is I over 10. And I'm saying steps of 10% in my hypothesis is going to be fine enough grained for me to have a look at this problem. Small I takes the value 0, 1, 2, up to 10. I'm going to use the principle of indifference because this is about my subjective belief, and I have no particular reason to favour hypothesis H1 over H7 or any other case like that. So I'm going to say 5.4j as a good starting point for me. Probability of each of these 11 hypotheses is 1/11th. They form a comprehensive list, and as far as I'm concerned, they're all equally likely to start with. Then I want to be able to use Bayes' theorem to update the probabilities for each hypothesis given our observation. And in order to do that, we need a model for the conditional probability of the data, that is, on meeting one couple, finding they're nice, in each hypothesis. So 5.4k, let's say the data, it's that, we meet one couple, and they turn out to be nice, and I need a model for the conditional probability of this observation, if the hypothesis H1, H2, etc. is true. You will hopefully agree with me. It is clear the principle of indifference applies to which couple you meet. So the probability of D in the ith hypothesis is just I over 10. So to pick an example, in my hypothesis H7, where I was 7, I said 7 out of 10 couples are nice. And in that case, given that I meet one couple, my probability that they are nice, I'm indifferent about which one I meet, it comes out as 7 over 10. That's my model for conditional probability of the data, 5.4L. You need to understand, well, you need to be happy about that being true in this example. You can read through in the notes. That should make sense. And so given that we have prior probability for each hypothesis or situation, and a model for the conditional probability of getting the data, that's all we need to apply Bayes' rule and update the probability of each hypothesis to obtain what's called its posterior probability, or its afterwards probability, in light of the data. And we do that as equation 5.4m. It will turn out, applying Bayes' rule, 4.6c, the probability of hi, given the data, it's this probability of data given hi. We have an expression I over 10 for that. Prior probability of the hypothesis, 1 over 11, and probability of the data, which, as we did before, we obtained the total probability of the data, 5.2g, based on the total probability on the prior beliefs of each hypothesis. So in other words, we use the law of total probability as in equation 5.4n to get the probability of the data, which comes out as a half in my 5.4m. Once I have all those numbers, I can evaluate the expression 5.4m for each hypothesis hi, and then I've got a new probability for each hypothesis or situation. And I was interested originally then in the question, most couples in Lake Wobegon are nice. Well, most of them being nice is equivalent to saying either hypothesis 6 was true, 6 out of 10 were nice, or 7 was true, 7 out of 10 were nice, up to H10, 10 out of 10 were nice. If I add together the probability of those hypotheses in my clearly slightly approximated model, I get 5.40. The probability of the statement I'm interested in this version, it comes out as 0.73. Just adding up the probabilities of the list of situations, the list of exclusive situations, hypothesis 6, hypothesis 7, up to hypothesis 10. Or if you want a more elaborate way of doing it, you could use equation 5.4p, and you could say for each of the 11 hypotheses, let me use the law of conditional probability. So for each of the 11 hypotheses, is it true that most of the couples are nice? But most of the couples are nice is a very simple behavior for each of the hypotheses. It's just a probability of 0, an answer definitely not, if between 0 out of 10 up to 5 out of 10, which isn't most, are true, and then it's plus 1, it's definitely true if between 6 out of 10 and 10 out of 10 are true. So that is the method, and with it you get, very pleasingly, you get a quantitative number for the answer to an apparently nebulous question, are most couples nice? You get an exact number, you say 0.73. If you follow through my particular bit of reasoning. Now let's add two bits of improvement that we could do to the solution method we just looked at. First of all, you might have said that when I was writing this solution, I used a very coarsely separated list of hypotheses, in which I said the situation in this town is either there's 0 nice couples, or 1 out of 10 couples are nice, or 2 out of 10, and so on. In other words, bins with a sort of 10% probability width. You might say that's too coarse, and I should have used much more finely resolved hypotheses. Of course, I could have done that. We could have said that it's 0 out of 100 couples are nice, 1 out of 100, 2 out of 100, all the way up to 100% of couples are nice. If we did that, we would get a slightly different numerical result. It would be, instead of about 0.73, which you get using the dividing into tenths, you would get a number which was close to 0.75 or 75% for your probability that most couples are nice. And so 0.75 or 75% would be a better answer from a finer resolved analysis. You could take that 2 steps further. You could say, why don't you use even finer grained hypotheses still? The answer would be you'd get an answer which tends towards 75%. Or, instead of using a list of hypotheses, you could ask, why don't we take this principle of taking a list of hypotheses and convert it into the algebra of continuous probability? You'd be right that that can be done, and if you do that, you take the principles in this section, but instead of having a finite list of hypotheses, you have to find a way to consider a continuous range of hypotheses. You can do that. You end up with the mathematics of beta distributions, which describes how this work is done using continuous probability theory. In this course, we will stick, in terms of what you have to do, to the list of hypotheses in the way that I've described here. That's because lists of hypotheses are nice and easy to conceptually, and they're easy to work with in a spreadsheet or a MATLAB script. It's not necessary, in order to get the principles of what we're doing, to use beta distributions, which you can look up in Berry's textbook or elsewhere. If we were to look at beta distributions in detail, this course would become much more of a maths course and less of a course about principles. But there, you know the name to look up if you were to want to know how to do Bayesian probability theory with continuous algebra. We'll stick here to the lists of hypotheses, and we shall look at another slide, because this question of how you do this processing of your data is one which often raises lots of audience questions. So we can look at how this is. If you're happy with the algebra, you could move on from here, but you might want a alternative description or visualization of the process that we've been going through. So I've got that here on this slide. As I said, we've got this concept of starting with a number of hypotheses, h0 to h10, and I said I was indifferent about them. So by being indifferent about them, we've got this graph at the top. So for each hypothesis in my list, h0 up to h10, my p of hi, my prior probability, is equal, and it's equal to 1 in 11, 1 over 11. That's a flat prior, it's called. And each one of these hypotheses represents along the top a possible physical situation in the town which we're looking at. So you've got couples who are in red with horns, not nice, and smiley faces, nice. Your representations here of a few of the hypotheses. The H6 is the idea that a representative population is drawn by this picture, where you've got 6 nice couples and 4 nice couples, and they're chips in a bowl, and you imagine reaching in and drawing a chip at random when you encounter a couple to determine whether and then you find out whether you've drawn a nice couple or an unpleasant couple. Obviously, in the case of H10, there are only nice couples to draw. Why, you might ask, do I have this list, with this case, of subdividing my situation in the town into lots of different hypotheses? Because the original question you were asked is it true that most couples are nice? So you might ask, why don't I write down my fundamental hypotheses, just H, most of them are nice, and hypothesis, most of them are not nice? Well, the answer is because the hypothesis that most couples are nice fails my criterion that I've got in section 5.4d, part 2 of the recipe, in which I said the hypothesis needs to be able to allow you to accurately put a number on the probability of getting the data. And in fact, most couples are nice includes hypotheses from H6, where 6 out of 10 were nice, all the way up to H10, where all 10 out of 10 were nice. So it doesn't let you put an accurate number, which should be as accurate at least as 6 out of 10, 7 out of 10, 8 out of 10, so on. With my finely divided hypotheses, I can put accurate numbers on the probability of seeing the data. With my coarse, kludged hypothesis, which I wouldn't use, just a two hypothesis space of less than half a nice and more than half a nice. That might seem closer to the hypothesis you want to know about for your conclusion, but you actually have to get them by considering a finely grained list of hypotheses. And obviously you just add up the probabilities of H6 up to H10 in order to get your probability that it is true that the situation is most of the couples are nice. You need to use a finely grained list of hypotheses. So that's why we have 11, or you could even, in a spreadsheet, no problem to consider 100 or 101 hypotheses. And the graph at the top shows your flat prior. The second graph, this triangle wave, is your likelihood of the data given each hypothesis. And if you do that, and you get this next slide, and we've got there all the information we need to use Bayes' theorem. You've got your at the top your flat prior, your probability that each hypothesis is true before you've learned anything. That's in each case 1/11th. Your probability of your data given the hypothesis is the triangle wave in the second graph there. Because you're meeting a couple at random, or you're drawing a chip from this poker bowl at random, so your probability of getting the data, which is that the one couple you met are nice, is just I/10. And if you plug that into Bayes' rule, you get the same triangle wave, except normalized, so that the sum of the bars amounts to a probability mass of 1. Same shape of triangle wave, but scaled. In your conclusion from your Bayes' rule, that is your probability of each hypothesis, given that you've received the data. So you meet one person and they're nice, that's an uprising triangle wave. If you program this in a spreadsheet and you look at some other cases, you'll find that this triangle wave is actually quite fundamental. If you meet one couple and you conclude that they're not nice, the way that your hypotheses would be affected would be a downward going triangle wave. And if you meet two couples and the first of them is nice, then you might update your degree of belief and you'd get the upward, the rising triangle wave for your degree of belief in each hypothesis. And you could actually feed that in as your prior on meeting the second couple. And if you multiplied that by what would, from the next bit of information, what would amount to be a downward going triangle wave, you would end up actually with something like this case. The graph on the left, that would be your a distribution for, well, I've met two couples, one of them was nice, another was not nice, and by applying the process twice that I showed you in the maths for getting the posterior probability for each hypothesis, you'd end up with this distribution, which it's actually a discretization of the beta distribution, but you'd end up with a lump of probability around. Well, yeah, the most likely situation says that about half of them are nice if you've met two and one was nice and one was not. Okay, you can download the slides and read more about that in detail. I will skip over, unless people really want me to do it in the comments, the business of this more uncertain than flat prior. You can read about that. Essentially, if you can in Bayesian data analysis, it's nice to start with some sort of list of hypotheses about which you're indifferent, because it's often very easy to conclude that you're indifferent about a list of hypotheses if you don't have any information one way or the other on them. And the flat prior is nice and easy to deal with mathematically. Sometimes there are situations where you need to use not an indifferent prior, but what would be called, what should really be called an informative prior, where instead of having a flat prior, I might have lots of probability mass somewhere. And a non-flat prior, which is a single highly peaked distribution, that's informative, and it causes your conclusion to be closer to the center of your closer to your original distribution than would be the case for a flat prior. You can also have a deliberate radical uncertainty prior, where you put heavy frequency mass at the H0 and H10 hypothesis. This would be easier to discuss in person, so if people want me to talk more about this later, then I can do, but it's not necessary for the processing which I want you to do as part of this course. This slide talks about, well, what if we, as I said, if you apply multiple bits of information, so for example, your prior information is that you're looking at something similar to a similar example, but this is tennis players, and you discover that player A has won 3 and lost 2 of the previous matches against tennis player B. Well, if you start off knowing nothing with a flat indifference prior, and you apply the method of updating with triangle waves that we discussed in the maths, if you apply that to your hypotheses with 3 wins and 2 losses for A, you would get this prior on the left-hand side for before you learn about the outcome of the next match. This might be the degree of belief you have in player A winning various proportions of the matches. As you can see, because player A has won 3 and lost 2, you should have no belief that the proportion of matches which A wins is 100% or 0%. All the maths should be somewhere intermediate, and you say, well, this is the shape of the distribution for their record is a little bit better than 50-50. Okay, so that's various things about probability distributions. Good. Great. Now here's a important real application of Bayesian inference. Let's look at Bayesian inference with 2 parameters. Now this will use the same strategy of the business of the list of hypotheses. We just need to do it in some questions in a more elaborate way. So here's an example of how you do such a case. So this example in 5.6a is about some measured apple tree heights. We are given a load of data. So the height in meters of 30 mature wild apple trees. The heights were measured, and the following sample was obtained. So there's 30 different numbers to the nearest centimetre. It is assumed, we're told in the question, the normal distribution provides a good model for the probability of a tree's height, taking a particular value, and that the height of each tree is independent. We want to estimate the parameters of the normal distribution from which this sample is obtained. We want to obtain the population mean mu and the population standard deviation sigma of the normal distribution from which these numbers were probably drawn. And we are given some helpful extra information to simplify the problem, to avoid having to deal with plus or minus infinities. We are told that the mean height mu of apple trees is between 5.5 and 7 meters, and the standard deviation is between 0.1 meters and 1 meter. So we're given that in the question. So all we need to do is the same strategy as before, writing down a list of possible hypotheses describing the situation. The hypotheses will describe the population mean and population standard deviation, which might take a number of different values. And we need to update our information about those, which might be an indifferent prior, because I have no particular reason to favour one population mean or standard deviation over another. I might use a flat prior for those hypotheses. And using our conditional probability for getting the data on each hypothesis, we just update and get a new probability for each hypothesis, and then we use that to compute something, in this case namely an estimate of the population mean and the population standard deviation. By the way, this kind of problem, a two-parameter estimation, the model contains two parameters. In this case they're both useful parameters because I've been asked to estimate them. If I was only asked to estimate the mean, the population mean, and I wasn't told that I had to do anything with the standard deviation, then the standard deviation would be a nuisance parameter. It's something that I have to estimate, but I didn't care about it. Anyway, in this problem as it's written, I'm asked to find both, so they're both important parameters. So normal distribution, so a bit of work here to turn this into a useful expression, but the simple expression we're going to use is equation 5.6 BB for the probability that you measure a height of a tree, capital X, to the nearest centimetre. A bit of faff about where this comes from. We're told that the height of a tree, capital X, is drawn from a normal distribution with the following probability density function. Small f of x, given the population parameters mu and sigma. That probability density function is 5.6b. But, of course, a measured tree height of 6.18 metres really means the tree height lies somewhere in the range of 6.18 metres plus or minus half a centimetre. So to get that finite probability, technically I ought to do some awkward work. I ought to integrate the normal distribution to obtain an expression for the finite tree height in terms of error functions. I could do that. We're not going to here. In practice, looking at the numbers in this example, in particular that our measured tree height is to the nearest centimetre, but the smallest population standard deviation is 10 centimetres. Therefore, the probability distribution f does not vary much over the range plus or minus half a centimetre, so it is sufficient for us to work with an approximation here, which is that the finite probability of measuring a tree height of, for example, 6.18 metres is just proportional to the probability density function small f from equation 5.6b at 6.18 metres, given the parameters. So, bottom line, we're going to use the following approximation to work with something that I've said is approximately normally distributed. We're going to say where a is a constant of proportionality, the probability that we measure a tree height capital X given the mu and sigma is equal to this expression 5.6 BB. I've just taken the normal distribution and I've put in a constant of proportionality a. That's alright, it's going to cancel out in the later maths that we do anyway. We're going to use the same inference strategy as before to get an estimate of the population mean, the height of an average tree in the forest. So we're going to consider that we have two parameters to worry about. We have the the mu, the population mean of the height of the trees. That takes a value, we're told, between 5.5 and 7 meters. So let's consider a list of possible values of mu. Mu I is 5.4 plus 0.1 I. That's expression 5.6c. Let's also consider a range of values of sigma. So sigma j is j over 10, where j is 1 to 10. That's filling up the range that we were told was possible in the model. And then let's say the hypotheses Our hypotheses Hij means mu takes the value mu I and sigma takes the value sigma j. There are 150 possible hypotheses because there's 15 mu's and 10 j's. 150 hypotheses. I have no clue if any of them are favourable, so I'll say I use an indifference prior. They each have a constant probability c, and that probability is 1 over 150, as given there in expression 5.6g. Just a moment. 5.6g off the bottom of the slide. Now, this list of hypotheses gives us a comprehensive list of approximations, which we need, and each hypothesis lets us compute quite accurately a probability for getting the data using the expression 5.6 bb. Now, the probability of observing the whole sample of heights, given the parameters, and given what we were told in the question, that the height of trees are independent events, is given by this expression 5.6h. So the probability of the entire data d on a particular hypothesis Hij is just the probability of a tree height x taking the value x1 on that hypothesis, times by another tree, a second tree, taking the height x2, times by expressions for each other tree height. Or in other words, it's this product of 30 terms written using the pi for product notation in 5.6i. That's okay, that's only mildly awkward algebra to deal with. We can apply Bayes' rule to this mildly awkward algebra to compute the posterior probability, a new probability given the data for each hypothesis. So the new probability for each hypothesis Hij given the data, it's this expression, the probability of the data given Hij from 5.6i, times by the probability of the prior probability of the hypothesis, which I just said was 1 over 150 for each of them, divided by the probability of the dataset D. The probability of the dataset D is obtained as a total probability using the law of total probability and mildly strenuous algebra. It can be computed once all of the values of probability of data given Hij are evaluated in some form. They could be evaluated as numbers in a spreadsheet, or we could deal with them to quite some extent algebraically. So your probability of the data on hypothesis Hij is given as expression, the probability of the data in total is the sum of the probability, the conditional probability of getting that data on each hypothesis, times by the probability 1 over 150 of that hypothesis. That's my 5.6k. So some notes here. So if my probability of my measured height, capital X, is given by expression 5.6 bb, then in my Bayes rule equation 5.6j, there will be a constant term, a to the 30th. And that will be in the term on the top, and it will also be in the term on the bottom. So the a to the 30 in probability of data d given the hypothesis Hij will cancel out with another term in the probability of the data d. So at some point there's an annoying constant which will cancel out, so you'll be able to ignore that. Second note, when you're doing computations with probabilities of getting a sample of data, often you calculate the log of the probability of getting the entire sample instead of the probability. That's because the probability is often given by a lot of small probabilities multiplied together, and if you keep taking 0.001 times 0.002 times 0.001, you quickly end up with numbers that are too small to be handled properly by the computer. So very frequently you have to, instead of multiplying together 30 probabilities, you work with the log of the total log of probability of data given Hij, and you get that by summing the log of probabilities of the individual measurements, as in 5.6L. So you may need to do that if you have moderately large data sets. And if you're if your probability for your individual measurements is given as it is in this example question using 5.6 BB, then your log of the probability of the data on hypothesis Hij is given by this expression 5.6 M. You might want to check that I've correctly expanded out the log of the expression I got from the normal distribution, and you see there's an A, but when you manipulate this expression, the A, when you manipulate this expression and you put it into 5.6J and work with it, the A will cancel out because it's just a constant of proportionality, which should feature in probability of D conditional on Hij, and also the same way in the probability of D. Okay. There's some algebra for you to read through. You should be able to get a graph that looks like this in MATLAB. Assuming you have MATLAB training, and hopefully you've come across the mesh grid function. If you haven't, look up the mesh grid function in the help file, because it's too difficult for me to describe without in-person discussion, or ask someone what the mesh grid function is. But what we've got here is I have a grid representing my 15 different mu values, which I said were possible in the hypotheses, 10 different values of sigma. Take those both and you have 150 hypotheses. We've plotted here the posterior probability of each hypothesis Hij, given the data sample of 30 measured tree heights. You should be able to get that, and you should be able to, given your probability for each hypothesis, you should be able to get an estimate for the population mean. An estimate for the population mean is called mu hat, as in equation 5.6n, and you just get it by saying we'll take a weighted average of which is the sum of the possible population mean mu I times by the probability of hypothesis Hij, summing over all the hypotheses. And we do the same for an estimate of the population standard deviation. Sigma hat, it's just the sum over the 150 hypotheses, the probability of the 150 hypotheses given the sample of data, times by the value that sigma takes in each of those hypotheses. If you do that for the sample of data I've given you in this question, you should get mu hat is 6.27 meters and sigma hat is 0.44 meters. This is nice because I know I got these numbers from simulated data, where I simulated the data using actual mu was 6.3 meters and actual sigma was 0.4 meters. So it's good that my estimates come out similar to that. Limitations of the normal distribution as a model for observed data. Well, many people assume the normal distribution is there's some theoretical reason why it is true of things you see in the real world. That's not necessarily the case. Very often the normal distribution is just an approximately correctly shaped single humped distribution, and it's good enough as an approximate description of data. It's got some mathematical flaws, however. The normal distribution does predict some probability, often a tiny negligible probability, but still some, for negative values of the data. In the case of tree heights, it's nonsense to say there's some, even a small probability that you have a tree of negative height. That's sometimes a problem. Not in this example question, but it can be a problem in other situations. The normal distribution also predicts very low probabilities for outliers. Many real-world distributions they have heavier tails. And sometimes if you need to model a problem, using a heavier tailed distribution of some sort, we won't go into what, can give you more robust behaviour, because it will be less, you will end up with a inference which is less badly thrown off by trying to cope with outliers. Okay, good. So we've looked there at parameter estimation with Gaussian two-dimensional, two parameters with a two-dimensional Gaussian. And a simple example. You should be able to work with that. Maybe use it in your assignment if you'd like to. In another year, I would probably talk at this point about the binomial distribution, but I won't talk about the binomial distribution because I haven't set something that depends so heavily upon it. I do need to talk about hazards of data analysis. Chapter 6. I will talk briefly this time about hazards, in particular the hazard of regression to the mean, or the regression effect. This, along with Simpson's paradox, is one of the bad things which can affect data, or data analysis. One of the most serious bad things. So, let me give you an example, some examples of what regression to the mean is, before we see how you check your data to see if it's present in your data, so that you can perhaps avoid being misled by it. Okay, so the regression effect. You might get some of the following stories told to you. So example 6.1a. A snooker player experiences a bad run of performance. He's doing unusually poorly in all of his games for some run. This prompts him to go to the shop and buy a new cue. And in the next few games, his performance has improved. It's back to his average. And he credits the benefit of the excellent new cue for this improvement. Could be true, but we'll talk about why it might not be true. 6.1b is another related example. A woman with backache visits an acupuncturist. Afterwards, her backache improves, and she tells everyone who will listen that acupuncture is a splendid treatment. 6.1c. I like this one because I more or less got this from a friend of mine who works for a county council that shall remain nameless. Following a spate of traffic collisions on a stretch of road, there's an unusually bad number of traffic collisions for a few years in succession. Speed cameras are installed. In the next year, there are fewer traffic collisions, and the county council awards a generous bonus to its director of road safety. Okay, a story you can easily imagine happening. Regression to the mean is probably involved here, but let's say in every one of these cases it's completely possible that the action that was taken did actually cause an improvement. However, another explanation is possible, and even likely, when you hear about these cases. It's the regression effect. The regression effect, it's easy to identify in some situations, and hard when people present a story like those above. What's very possibly happening, by the way, in each of these cases above, is that you have something a bit like a sampling bias. Well, in each case, you have a particularly bad... So you have a situation, performance of a player in a snooker game, the state of health of some person's back, and the number of traffic collisions. In each case, these things probably naturally vary a bit from time to time. And in these examples, somebody has taken the fact that the situation is extremely bad to do something, and then a bit later the performance is back to average. Well, it was very likely that performance, if it was just naturally randomly varying, was going to be closer to its average than the extreme bad value that prompted the action. It's very likely that was going to happen even if there was no improvement caused. So was there some improvement caused? We need a way to study whether this is the case, whether our data might contain regression to the mean, causing us to misattribute causation, possibly. So, mathematically, first of all, let's think about we just did an example on the heights of trees, and we said the height of trees, in our example, we were told these are independent. So, suppose that you measure the height of one tree, and it turns out to be in the top 10% of tree heights in the population. Now, clearly, there's a high degree of probability, at least 90%, that the next tree height will be smaller. This would happen even if there was no physical cause, like someone going along with some pruning shears, trying to spoil your run of tall trees. That's the regression effect. Let's see if we can see this as an effect that's generated or caused by a particular kind of data generating mechanism. So let's imagine 6.1e. This is a mathematical example. I probably have a MATLAB script for this, which I can probably put up. Okay, I've put up a zip file on Moodle containing a MATLAB script labelled with regression to the mean that's got this example in, and a previous example, if you want to muck about with the script for generating these graphs and these examples. Might be helpful. So 6.1e, a set of bricks have masses of exactly 3.00 kilograms, 3.02 kilograms, 3.04 kilograms, etc. in increments of 20 grams up to 4.00 kilograms. Each brick is weighed twice. Each weight measurement has some error, and the errors are independently, and in this case identically normally distributed. Each of them has a rand n error on the measurement. The mean error is 0, and the standard deviation is half a kilogram. And the observations are plotted in 6.1f. What do we have in 6.1f? Figure A, so the left-hand side, is simply the two measurements. Two measurements of each brick are shown as blue circles. If there was no measurement error, of course, these circles would lie on a straight line, a straight diagonal line between 3 kilograms for both measurement and 4 kilograms for both measurement. Because there is measurement error on both, in fact, the best estimate of the the best estimate of the true mass is less extreme than the measured mass in each case. What do I mean about that? We know, I've told you in this example that the masses are between 3 and 4 kilograms. Consider your mass measurement number 1. There's a number which are above 4 kilograms. You know those contain a positive error contribution, given the setup of this problem. So anytime you have, so if you're in these high mass measurement number 1 values, you know that there's a positive contribution from error, but you also know that the error was normally distributed with mean 0. So your best estimate of the true value, which should be on average measured by the second measurement, is less extreme from the so less extremely high if we're looking at mass measurement 1 is bigger than 4 kilograms. And in fact, you have, this is what your vertical least squares linear regression line, your red line, gives you your best estimate of the your estimated second mass measurement, which is itself unbiased, given the first one. The measurements, however, that you can also compute the correlation coefficient, and you'll end up with r is plus 0.35. Well, it's good because there are actually a range of different masses of brick, and the fact that you've measured them twice with some error, quite significant error, well, still nonetheless, the heavier bricks do tend to be heavier than the average brick on both measurements. It's just that both measurements have a big spread on them. So your one regression line, minimize your vertical square errors is the red line, minimize your horizontal square errors is the black line. So the red line is your prediction of M2 given M1, and your black line is your prediction of M1 given M2. Okay, that may or may the business of correlation lines, regression lines. That's indicative that there might be regression to the mean. in this. Certainly they are different in this case because both measurements contain some random variation. How do we show that regression to the mean may well exist within a scatter plot of this type, or within data that gives you a scatter plot of this type, because you've got two measurements, each of the same thing? Well, the way that you do it is, well, first of all, let's say the regression effect, if you want to give a nice short definition, 6.1g for two correlated measurements, x and y, of the same type, like two mass measurements of the same brick for a number of bricks. The regression effect is whenever x is larger or smaller than its mean, y tends to be less extreme than x. So if you want to identify the regression effect happening in data, you can do it as follows. To show the regression effect when y is positively correlated with x, plot y minus x against x, and show that those are negatively correlated. That's your recipe. If y minus x is negatively correlated with x, that means bigger x, or x bigger than average, corresponds to less extreme y. And that's exactly what I've plotted here on this graph B. We've plotted mass measurement 1, and then that's effectively x in the language of the notes down there. And then mass measurement 2 minus mass measurement 1, that's y minus x. And you see these are negatively correlated, so in other words, mass measurement 1 bigger than its average value corresponds to mass measurement 2 being less extreme. In other words, very likely some regression to the mean is going on here. And that's how you identify whether regression may be affecting your data. At least if you've got nice, well-behaved data from an experiment, which goes into the form of a scatter plot where you can easily do this sort of thing. If you've got data from the human world of the type like the snooker player's performance, heavens knows how you deal with it. But there we've described briefly the regression effect and said a way of identifying it, whether it might be a problem. We'll talk briefly last time about a famous observation by a guy called Daniel Kahneman of the regression effect leading to bad behaviour in teaching environments. We'll look at that though next time, because we've now looked at enough maths, quite enough maths for this time and for doing the assignment.